A uniform cylindrical block of length L, density d1 and cross-sectional area A floats in a liquid of density d2 contained in a vessel. d2 is greater than d1. Okay, so it means that the density of the liquid is greater than the density of the cylindrical block. The bottom of the cylinder just rests on the spring of constant K. The other end of the spring is fixed to the bottom of the vessel. The weight that must be placed on the top of the cylinder such that the cylinder is just submerged in the liquid will be equal to. Now over here in the first case, when it is very much clear that the bottom of the cylinder just rests on the spring of the constant K. It means that the spring is exerting negligible force or almost zero force in this case. Okay, so now in this case, in the first case when the block just rests on the spring, what are the forces acting on the block? mg will be in the downward direction. There will be buoyant force which is exerted in the upward direction. Okay, and since the block is in equilibrium, I can say that the force that is acting in the downward direction will be equal to the force that is acting in the upward direction. The force acting in the downward direction will be equal to mg. Force acting in the upward direction will be equal to buoyant force. Now let us say of this entire length L, only L1 is submerged inside the liquid. Okay, only L1 is submerged inside the liquid. So force that is acting in the downward direction will be equal to density of the solid or the block, cylindrical block, which is equal to d1 into volume. Volume over here will be equal to A into length into g. The buoyant force that is acting in the upward direction will be equal to density of the liquid area into the L1 length that is submerged inside the liquid into g. So over here g and g will get cancelled out, A and A will get cancelled out. L1 over here will be equal to d1 divided by d2 into L. Okay, d1 divided by d2 into L. Let this be the first equation. I will use this later. Okay, after that it is given that certain amount of mass, let us say m, is added on the top of the block. Okay, such that now when I add mass m on the top, it will push the cylindrical block inside the liquid. So in the second case, what will happen is, now when the cylindrical block is pushed inside the liquid, the scenario will look somewhat like this. Okay, the mass m is added on the top. Now the entire cylindrical block is submerged just inside the liquid. Okay, is submerged just inside the liquid. So in this case, what will happen? Now the length over here is equal to L1. So now the remaining length will be equal to L minus L1. Now you can clearly see that the spring is compressed in the second case. By what length is it compressed? Now the entire length, the cylinder over here had a length L. Of that, L minus L1 was floating outside the liquid. Now when I put a mass m on the top of the cylindrical block, it means that L minus L1 has gone inside the liquid. It means that the spring has been compressed by a length of L minus L1. Okay, now what are the forces acting on this block, on this cylindrical block? Okay, so now over here mg will act in the downward direction, capital Mg will act in the downward direction. Since the spring is compressed in the downward direction, the spring force will act in the upward direction, which will be equal to k into x. X over here is equal to L minus L1, and the buoyant force will be acting in the upward direction. Let us see on what part of the block will the buoyant force act. The buoyant force will act on the entire length of the cylindrical block, because now the entire block is submerged inside the liquid, but there will be no force acting on the mass that we have added new. Okay, the new mass that we have added. The reason is very simple, because the mass that we have added newly is not inside the liquid. So in this case also the total downward force will be equal to total upward force. So mg plus mg, that is the total downward force, will be equal to total upward force, which will be equal to buoyant force plus the spring force, which is equal to kx. Now we have to calculate the value of mg. Okay, that is the weight of the block added. So it will be equal to buoyant force plus kx minus m into g. So now let me substitute the values. Buoyant force will be equal to density of the liquid, which is equal to d2, area. Now since the entire length has been submerged inside the liquid, so it will be equal to L into g, okay, minus mg. Okay, I will take minus mg prior to the kx. Okay, So it will be equal to density of the solid, area into length into g, okay, plus kx. Plus kx over here will be equal to L minus L1. So it will be equal to L minus L1. So now I can take from this, I can take A, L, G common. It will be equal to d2 minus d1, okay, plus k into x, okay. Over here plus k into x, it will be equal to L minus L1. Now L1 over here will be equal to d1 by d2 into L. So it will be equal to d1 divided by d2 into L, okay. So from this part I can take L common, okay, I can take L common. It will be equal to from the entire term I have taken N common. It will be equal to Ag d2 minus d1 plus k d2 minus d1 divided by d2, okay. So over here I can take d2 minus d1 also common. So L d2 minus d1 a into g plus k divided by d2. This will be the total weight added